All right, so I want to break this into two parts. The first part we'll just talk about schematic capture and how to, just the basics of working around a schematic. Then we'll move on to setting up a PCB and then some very basic, mostly focused on setting things up, not really focused on the design of the PCB, but there will be some elements in there with that. So I've already started a schematic, not quite finished, but it's just some really simple little thing. What it's going to be is it's going to be a breakout board for an STM32 F103C8. This is a really popular microcontroller. You can buy breakout boards for this thing for like $2. It's pretty crazy. And a good deal for sure. And it's a nice microcontroller, I think. We use it a lot. We use a lot of microcontrollers in this family for various things on at CWRUbotix. So I've made most of the schematic. I won't go into details on everything, but I think it kind of speaks for itself. But there's a few things we need to do. First of all, usually you don't just start with the schematic. Usually you'll start by making a project. So that's what we're going to start with. I'm going to go to File, New, Project. And the project type, PCB project, that's what you want. Give it some kind of name. I'm going to call it the Crew Pill because the dev boards that you buy are called the blue pill. Because they're blue and I don't know, people like the name. So they're popularly known as the STM32 blue pills. So we're going to make this and call it a crew pill. So we'll go to resources. I'm just going to make this on our Google Drive. Where should I put it? I want you guys to have access to this too. All right, now I'm going to move this file. So I just made this as a free document. We're going to move this file to that location. Sorry, this is just me navigating the file system. Oh, I goofed something, whatever. Yeah, it made a folder for the project. So that's good to know it does that, I guess. So now that I have an existing schematic, ordinarily you would then right click on the project and say, add new to project, add new schematic. Instead of doing that, we're going to add an existing schematic to the project. And we're just going to add that document that we just saved. So now you can see our project down here in our projects pane as the CWRUbotix crewpill.project PCB, all that stuff. So let me just make sure I've got the correct file open. Okay. And
on that file in the drive.
What's that?
The file is in this
Yeah, it just has to synchronize, but in about 5 seconds it should be on the drive. Yes.
Okay, cool.
So yeah, if you want to take a second and grab that off the drive so you can kind of follow along if you like, you can do that. But I'll go ahead and just continue here. So I've got my schematic as part of this project. So now we can start our design work. You've all got the components tab, or you've now got your libraries installed, so you can find many components of many types. And hopefully everything is just kind of self-explanatory, that you can find things based on their category. So that's when I want to add a component. Let's say I want to add some resistor. My preferred strategy is to double click. I know some people like to click and drag, but I like to double click and then drop it down. So I've got a few different, I'm not going to go into detail on this design, but I've got a few different things going on. I've got two different power domains. One of them is is just called the VCC Power. The idea being I'm going to take, this is like the Arduino-esque thing where you can put in some variable voltage and it drops it down to the system voltage. So I've got that there. Imagining I didn't have that, you would go up in this little toolbar, right click on it, and you right click and it gives you more options. So I want to place a VCC port here. The thing about power ports is the power ports jump across schematics. So if you have multiple schematic sheets in a project, those power ports carry over and are common across all schematics. The next thing I want to do is I want this this node here, which is lighting an LED. I want to also have that on the pin headers over here. So the way I would do that, I don't want to draw a wire because that's kind of messy. So I want to name this net with some name. So you go up here to this symbol and right click, and you can hit net label, and that's what I want. So now while I'm still, like when I haven't placed it yet, I can hit the tab key and the properties tab pops up for me. And I can type in what I want it to be. So I'm going to call it C13 because that is the naming of this for the microcontroller. Let's change that. Now I click to place and you can see where that little X is when I was placing it. That little X needs to intersect the wire so that I can, it'll logically be connected there. So now I'll go ahead and Control C, copy this, and paste it right over here because I want it to be connected to pin 17 on this header. So I need to draw a wire between this label and this pin. And you can do that up here in this toolbar. It's the same place as the net label. Right click there and hit wire. You can see now that I'll just place a wire. And making sure that I have the wire intersect right where that logical connection point of the label is. Okay, and I connect it over. Now that is logically connected to that pin. Great. Now, do I have anything else I need to tie up? I think we're probably good. You can see I've used, I did miss something. I need A11 and A12 to actually go to the microcontroller. So I'm going to jumper those over here. Here's a nice shortcut to make a wire. If you hit P, it brings up the place menu. And then if you hit W for wire, you get a wire. Now I can place the wire. Now I need to copy paste this label, paste it down. Okay, now they're connected to the micro. Great. Also, yeah, sorry.
So back there was always A11 and A12. Are they different or?
A11 and A12 are different nets, yes.
Well, right above the A11 you place on the controller port 33, there's a A12. So right above.
Oh, you're right. Sorry, I'm blind. I'm sorry. That's my mistake. But I am missing something. These actually those are the same. Sorry, that was very confusing, I'm sure. Pin A11 actually does connect to pin A11, sorry. What I meant to do is grab these two here. These are the programming pins. Those are supposed to go up here. Okay. Does this make sense now? I hope that cleared up.
Yes.
Sorry.
Yeah.
That was confusing indeed. Yeah. Okay. Sorry about that. So now I've placed my nets. The process would have been the same, copy pasted them down. A11, A12 are supposed to go to those and not those, yes. Okay. One other thing I got to do, I've got to tie up this over here. So now, if I look in my power port list, there is no power port called 3v3. But if I take any one of these, whatever style of power port I like, and I'm going to place it and I hit tab, I can now edit the name of this power port to make it 3v3. So now that assumes the name 3v3. I place that, and then I've got to grab a ground port and place that, and that's that. One thing you'll notice at this point is that every component has a little a designator, but every one of them just says, has a question mark after it. And that's not good because I can't refer to U2, I can't refer to my components by their reference designators. So there's a really easy tool to use to annotate. It's called annotating your schematics. If I just go to Tools, Annotation, Annotate Schematics, I get this window that pops up, and it gives me a list of these proposed changes. First I'm going to, basically, most of these tools you'll never use. What you care about is you want to update your changes list. It says, okay, a bunch of changes are made from previous state. Okay. Now it'll actually show you which each designator is going to be turned into this numbered designator. Then I have to hit accept changes. Then it gives me this, this new window. I can hit validate if I don't trust it. Everything gets validated. And this is what actually annotates it, hitting execute. Then it actually does it. Close this, close that. Now we go back and look, every component has a unique reference designator. So that's an important step that you have to take. You have to make sure your schematics are annotated with
What's the
unique.
U flag mean?
Sorry, can you say again?
Yeah, so I know that like C is capacitors, D is diodes, but then all the boards are labeled U. What does that
Yeah,
stand
all
for?
the little, it's sort of a historical thing. I don't know exactly the history of why it is, but integrated circuits are typically designated with a U. I think it's for uncategorized or undefined or something like that.
Cool.
So that just means that when you see a U, that typically just means some integrated circuit. Now, some heathens out there like to actually call them IC, like IC1, IC2. And that, while that is very sensible and reasonable, there's conventions that have been built up over many years, and for no reason at all, we call them U. So when you manage your company's Altium library, you can call it IC whatever, but I use U. Yep, U. Yeah. So reference designators. Now we've annotated our schematics, and we have our nets all named. Everything's connected up. There's one other thing I want to do, which is a little bit of an extra thing. These USB lines, ideally, they should be differential pairs. So I need to tell the schematic that these are differential pairs. There's two things you need to do. One, you're going to place a parameter set. Right-click here and hit differential pair. Place that parameter set on both of your differential pair lines. Then the critical step is we have to follow a particular naming convention. Basically, you give the net a name like USB, then you give it an underscore P for positive. Sorry, I don't know if the capitalization actually matters. You give underscore P for the positive line, and the same net name, but with an underscore N for your negative line. That is how you designate positive and negative of a differential pair. We'll see how this pans out later in the board. But this isn't super critical even, because this is just This is just a low speed or USB full speed, so it's like 12 megabits per second, which is nothing crazy, but I'm going to do it just for as a teachable moment. Save our schematic. Okay. I think we're done with the schematic. So once you do the schematic, you'll do a schematic review and make sure that everybody likes your schematic. Then you can move to the PCB layout. And that's what we'll do now. So right click on your project, go to Add New PCB. And it does things, and you get a PCB. First thing we want to do is save it. So go ahead and save it in that folder that we made. Call it whatever you like, something descriptive. I'll just give it the name of the project, CWRUPIL. And now, before you do anything else, there's a sort of a list of different setup steps that we have to take. The first setup step that I like to take is, you can see the units right here, they're in imperial. And a lot of people still like to work in inches and mils. A mil is 1,000th of an inch, by the way. So some people like to work in imperial. I'm not one of them. So while I'm here, click anywhere in the project and go to Properties. And you scroll down in your Properties tab and you change the units to millimeters. And that's it. Now you can see this little window now has X and Y in millimeters, and everything's in millimeters. Great. The next thing I want to do, you don't have to do this, but I like to change the position of my origin to be the position of the origin on the board. We'll resize the board later. It's just giving us some random size pretty much. But I like to put the origin right there at the corner of the board. And there's actually kind of a strange reason that I also do this, which is that components, you can't actually move them to the left or to the bottom of the original origin point. I don't understand that constraint whatsoever, but that is just a constraint of the software. For some reason, the component cannot be placed to the left or bottom of the original origin. I can prove it to you, and I don't understand why Altium is like that, but it is. So if you ever want a connector, say, hanging off the board by a millimeter, if you start your board at the original origin, well, I can't have the connector hanging off the board because I can't move it to the left or to the bottom of the original origin.
Sorry,
So,
how'd you say to switch the origins?
Yeah, I haven't switched it yet. Sorry, I've just been talking. Yeah, so I switch the origin. I go to Edit, Origin, Set. Then I zoom in to make sure I'm right there and set. Now the origin appears there. I could set it anywhere I like, but this makes sense because X is in the positive, positive X is going to the right, positive Y is vertical. So now the origin is set right there. Great. From there, I think we're good. We can now proceed to import all of our components. So we will go to Design. We're going to import changes from the project. And now you can see all the changes that are going to occur. This is all fine. Let's just go ahead and hit Validate just to make sure. You notice this shows up because it hasn't found, you haven't added any nets into your document, so it's going to throw an error here. But once we hit execute, it executes successfully and it's fine. So the first thing you'll notice is that all the parts are in this sort of red rectangle. And this is called a room, which is a sort of a construct in Altium that is used for logically and in some ways physically grouping components together. But I'm not a fan of using rooms. I think the rooms are there are other ways that I find more useful to logically group components. So go ahead and select that red rectangle and hit delete. Get rid of it, because I don't use it and I don't find a need for it, so we will delete it. The next thing you'll notice is that there's a bunch of errors here. There's a bunch of green, which is indicating errors. What it thinks is wrong is it thinks these pads are way too close together. But they're actually not, because the concern is its manufacturability. So Altium has a bunch of what are called design rules that it applies all the time. And it's throwing an error because our design rules don't fit the actual constraints of our manufacturer. So this is easy to change, and changing is actually fundamental to your job as a PCB designer. So what you do is you go to design, then you go to rules. And you can see there's a great many rules, and there's all these rules and rules upon rules, which is great. You can configure everything to your heart's desire. So the two big things that you want to set right up front are going to be your clearance and your width. Now, depending on this is going to depend on like your manufacturing tolerances. So let's take a manufacturer, for example. Let's say you want to get this made from JLC PCB. If we go to JLC PCB, we can look up their capabilities right here, capabilities. So what we care about are initially here for initial setup, we care about track width and track space. So we scroll through their all this stuff. Oh, and we will care about drill hole and size. Let's start with track space. The minimum track width and spacing. For 1 ounce copper, let's say our board is going to be 2 layers just because it's a really simple board, so it just needs to be 2 layers. So what do they say? Minimum trace width is 0.127. Minimum trace spacing is 0.127. Great. Well, now we know that, we can apply that to our design rules. So back here in Altium, let's go to clearance. Get a nice little interface here. I'm going to change my clearance. I don't want to go all the way down to 0.127. I'm going to change my track space to 0.15. So track to track, 0.15. Pad to track, I'll do also pad to pad and pad to track, I'll do 0.15. Through hole pad to everything else, 0.15. Via to everything else, 0.15. Now, here's an interesting one, copper. The most, like, it's just talking about all the copper, like flood fills or regions or anything like that. And it's saying 0.254. That's, the thing is, I don't know, I'm not sure I want to make this smaller, because when I flood fill the board, that is all the extra copper gets flood filled and used up. I'm not sure I want all the copper to be 0.254 or sorry, 0.15 millimeters away from everything else. I'm not sure that I want that. So I'm actually going to leave this as is. I'll make it some even number like 0.25, but I'm going to leave that one as is. And then text, we don't really care about text. So you could make this 0. And the reason I want to do that is so that it doesn't potentially throw an error when I have text that's really close to other text. So there we go. And these don't take effect until you hit apply. And then I hit OK, and look at that. A bunch of errors went away because they no longer violate the constraints our manufacturer set. So we're good. All right, let's go back here and let's do the width of our traces. Routing width. And you can see we have 2 layers. You can set the minimum. Minimum, again, let's not go all the way down to 0.127. Let's go to 0.15 millimeters. And let's make the preferred width 0.25 just because I want it to be all metric. And this is an odd one. For some reason, I don't really understand it, but Altium has a maximum width constraint. And I don't know when this would ever really matter, but if you want to make a wide trace, which you do frequently want to make a wide trace, you need to make sure this maximum width is set to something much larger. So, you could easily be making a 3 millimeter trace on a high current board. So let's make this like 10 millimeters. There's no reason to limit yourself on maximum width. You won't practically will not be placing a 10 millimeter trace, but also you don't want to restrict yourself if you're making a 1 millimeter trace. You don't want to. I don't understand why it's here, but it is. So you got to make sure that you set that. All right, so those are the big ones. Let's also jump in here and look at via size. Because via size is really important too. And it's here under routing. Go to routing vias. It does give you some, basically this is kind of a large via. This is kind of a large via that they have. Let's go back again to JLC PCB. Let's see what they say about their vias. What kind of vias will they allow us to make? So a via, does everyone know what a via is?
That's what I just asked, yeah.
Ah, yeah, sorry. A via is how you connect two layers together. So basically the way you do it is when they're manufacturing the PCB, after they've laminated your layers together, they drill through the whole board, and then there's a final step where they plate everything up. They add a very thin plating to everything. That plating process gives you a plated through hole, and those are your vias. So a via is a plated through hole from the top of the board to the bottom of the board, and through all the layers in between for that matter. Now it's true, while we're looking at this page, you can kind of see a cross section here that they have, this little cross section of a board where they've got some via samples. And there are such things as blind and buried vias. The bottom line is those are, well, first of all, JLC is not supporting blind and buried vias right now. So it doesn't matter anyway if we're getting our boards from JLC. But they're also more expensive. Any manufacturer that you get your boards from, the price could go up by 10 times when you ask for blind or buried vias. If you need them, you really need them. But on 95% of designs you will ever do, you do not need blind or buried vias. But blind or buried just means that it doesn't go all the way through the board. But like I said, pretty much all the vias that we work with, they're just all the way through the board. So there's two different numbers that you care about with the vias, and that is the drill size, because they literally have to have a drill bit which drills through the board. So there's a minimum via size. And then there's a minimum annular ring, which is the ring of copper around the drill hole, which directly influences the diameter, of course. So the reason this exists is just due to the accuracy of their drilling machine. Because if their drilling machine is a little bit off by a tiny bit, it could, I'd have to draw it to really illustrate this. But if it were drilling, off center, it might cut away that little section where your track interfaces to the via, and you can, you lose not only reliability, but you could totally lose the connection to the track, and it would be a bummer because your board wouldn't work, and you'd wonder why. So we have those two numbers for us. Two numbers are via diameter that is the pad, the whole ring, the outside of the ring, and the drill size. And JLC tells us that they'll manufacture a microscopic 0.2 millimeter drill. And you know, that's not actually like microscopic. There are vias can be manufactured smaller than that for sure, but that's pretty small. Like, it's amazing that they'll do that without an extra cost. Well, actually, they don't say it's not an extra cost, but I think somewhere they actually say it. So they'll go down to 0.2, and we can actually go down here, minimum via hole size. It says for single and double layer, minimum via hole is actually 0.3. Okay, good to know, because we're only doing a 2-layer board. We're not doing a 4-layer board, 4 or 6 layers. So we're actually constrained to 0.3 millimeters. Great. So let's set those some things. Our minimum via hole size is 0.3. Maximum, so their maximums, let's see what their maximums are. It says their maximum drill size is 6.3 millimeters. That's a mighty big via. I don't think we'll be making that, but let's set it anyway. 6.3 millimeters. And our preferred size. So just once we get onto the board, you'll see how big these things are compared to your parts. But like a 0.4 millimeter drill is reasonable. So let's look at our diameters. As it pans out, a 0.6 millimeter diameter is really what we're going to be looking at as a minimum for the 2-layer board like it is. The maximum, again, it's like this could be anything. You know, even if you have a 6.3 millimeter drill, you can have a huge pad. It doesn't matter. So let's make it something ridiculously large. But the preferred size, I'm going to make 0.8. So we have a drill, our preferred drill is 0.4, preferred diameter 0.8. That gives you an annular ring of 0.2 millimeters, which is fine. Apply that and say okay. All right, let's take a breath. Now we've done all of our setup. We can now start doing things like positioning components. Usually PCB layout or design breaks down into 2 stages. Your layout, which is positioning all the components, then the routing, which is connecting the parts together with copper. And I'd say your layout stage takes 90 to 95% of your time. And then the rest of it, the other 5 to 10% is spent routing. So you can use that as a predictor of your time spent. And, you know, so don't be afraid of routing, and don't use the auto router. There is a tool that you may have heard about or you may know about called the auto route tool. Yeah, it's right here, auto route. I'm sure that Altium has spent a lot of money developing the auto route tool, and I'm sure it's going to be just fine for simple boards. But I also think that the results will be obvious when you've used an auto router. And I think there are very specific cases where auto routing is useful, mostly which have to do with, you know, thousands of pins, and when you're doing pin swapping between your different GPIO banks and very complex designs that demand using an auto router. There's a time and a place for the auto router. But on a simple board like this one, it's really not worth it. And it honestly, what it does, it makes you look lazy and like you don't care about your job. Like being able to lay out and route a PCB is your job security right there. You know, don't throw it away and be lazy, because your manager is going to look at that and say, you know, this board isn't that hard. Why did you auto route it? It looks like crap. And, you know, it's worth your time to learn how to do it yourself.
Is auto routing just like really inefficient, or like?
I don't think so. I think it just produces sort of bad results. The results aren't particularly good. And yeah, there are certain inefficiencies, depending on how you want to define efficiency. It won't necessarily make the shortest path. It won't necessarily prioritize certain nets to be shorter than other nets. Unless, to properly use the auto router, there's a ton of setup that actually is required. The way that most people use the auto router is to use not a lot of setup, and then they just auto route it. And one of the problems is like all the traces are going to be the same width, which is if you don't set it up properly. You have to do a significant amount of setup to properly use the auto router. But you don't necessarily want every trace to be 0.25 millimeters. What if I want my power traces to be 0.5 millimeters or thicker? And what about, like, let's take my linear regulator here. Yes, there's a pad here that's 3.3. This pad is 3.3. Logically, they need to be connected. Physically, what I'm going to do is I'm going to draw out a copper region around it that's going to help dissipate the heat, because this thing is going to get a little warm. So it's, there's things that you need to think about and consider that the auto router won't do for you. So the auto router, used properly, can produce good results, but it often takes more time to set it up properly than to just do it. So that's my diatribe on the auto router. I just think you also, you learn things about your design. You learn how to think about, electrical design and how the board's going to go together when you do it yourself. So yeah, and furthermore, I think just the arguments of time saving, the auto router saves you almost no time, because you've already spent all this time making a nice schematic. You've done your schematic review. You've laid out the components on the board. You've done all these things, and now there's less than 5% of your time left is going to be spent routing. Is it really worth it to leave your design work to a machine? It's going to be up to you one day, but my opinion is that you should do it yourself. So let me see, what else do we want to talk about here? We talked about design rules. I should talk about how to define your board size and everything. That's important. I'm not going to spend a whole bunch of time on this. But I'm going to get a rough board size, and then I'll show you what to do. So I lay out my components, and I start laying it out, and I see, okay, this is going to be about this big, and this is going to go over here, and I'm going to need some space in here. And all right, great. Now I know how big it's going to be. I want to switch to one of my mechanical layers. Usually I use mechanical 1. I'm going to use the place line button to place some lines. Starting at the origin. As you're drawing, go ahead and hit Tab and change this width to something unique and small, and you'll see why. I'm going to make it 0.05 millimeters. Yeah, it's like hairline almost. So I'm going to go ahead and draw it out to, let's make it 30. I forgot something. 1 second. What you'll notice is that the grid size, the grid pattern, is kind of goofy at the moment. And as I was placing that line, you can see the issue. It just reminded me of it. I wanted to make the board width an even 30 millimeters, but I can't seem to quite do that, because look up at the top. It's jumping between 29.972, and then I jump one more grid and we're past 30. This is a problem with the grid size. So I'll jump up. You won't actually see it unless you enable the right toolbars. You need to right click on your toolbar space and hit this utilities thing, select utilities. And then I'll get this symbol here, which is a sort of a grid symbol. I hit grid and just hit set global snap grid and type it in yourself. I usually like to work with a 0.05 millimeter grid. You can work with, you know, whatever grid works for you, but you'll start with something like 0.05. All right, now we can place our line. I'm going to make it an even 30, like I said. This time I can actually hit 30 exactly. Now I'm going to want to do a double click to place that point. Otherwise, it's going to try to chamfer the edge and everything. All right, now we see, let's see, how tall do we want to make this board? It looks like it's going to end up being about 50. So this step that I'm doing here, you may choose to do it later in your design when you have a better picture of how big the board is going to be. But I'm going to do it now because I wanted to show you how to do it. So I double click again to place the corner. And finally, we scroll to the bottom. And I double click to end, escape to end the tool. Now I have 4 lines defining the outline of my board. Now there's a few ways you can, what you need to do now is select all the lines. And I was going to say there's a few ways to do it. One of them is what I just did, which is I held down the Shift key to select multiple things. Then I just dragged my cursor over everything and selected it. That's technique number 1. Technique number 2 is you select one of the lines, you right click and hit Find Similar Objects. Now I can say, what objects do I want to find? Well, I want them to be tracks. They have to be on mechanical 1. They have to be of a width. I remember I said make that width something unique. Make sure that width is unique. So now I can pick all the lines with the same width. I hit OK, and it shows me everything it's selected. Lo and behold, it has selected our board outline. Great. Now I'm going to go to Design, Board Shape, and hit Define from Selected Objects. Boom, now we've got a tiny board. I'll probably want to move all my components over. And then I get to work. I lay this out, lay everything out, get it to where I like it. Then there's 2 tools that you really ought to know about. Well, there's more than 2 tools that you should know about, but 2 tools that are good to know about are the Place Track tool and the Place Region tool. So they're a lot like they sound, but I'm going to take the example of this linear regulator. So I can, of course, connect things with tracks. Again, in this toolbar, you can hit this tool, Interactively Route Connections. And that'll allow you to take a track and route it to stuff. You can see it kind of helps you out a little bit. You can do whatever you want, you know, write your name with it, whatever. And this is a part of a differential pair, so it's complaining. But the other tool that I really like using is the solid region tool, because sometimes you just want to draw out an area of copper just to exist and have a net. So like I was talking about under my linear regulator, I'd like to have this section of copper just help dissipate the heat a little bit. Yeah, and it depends on how much board space you can afford. Oh goodness, this is terrible. That's okay. Just rough out the shape. We'll fix it in a moment. Now I can drag around the edges. Here's a hotkey that you should know for working with regions and polygons. As you're dragging a corner, hit the shift, hold shift, and then hit space. Now you can change the style of the corner modification. So I'm going to change it to this style because I want to. Now let's make sure these are both like, this is like sized reasonably. I can resize it to my heart's desire. Make sure this is good, looks pretty symmetrical, looks pretty good. Great. So there's an example of what I might do for a linear regulator like this. The other thing I want to show you before we wrap up, because I realize we've been here for quite a while, is the Polygon Tool. Once I've got all my components on the board, let's just place a few just to show you what's going on. So I've got a bunch of stuff on the board. Let's say I've done all of this and it's all routed. But let's say there's one thing I didn't route, which was ground, because there's so many pins that are connected to ground. Ground is like the most common node in your circuit. I mean, it's the whole reason there's a special symbol just for ground, because it's the most common node in your circuit. So you just give it a special symbol. In the same way, it's very convenient for us to tie up all the ground connections. And in the same stroke, we want to, use all the copper that is on the board. Because you're paying for an entire board covered with copper, so you might as well get your money's worth. So what you will do is go to Place, and make sure, oh, by the way, these are down here on the bottom, these are your layer selection. This is your layer selection bar. Like when I selected mechanical 1, so I could draw those lines. Similarly, when I want to draw, say on the top layer, I hit the top layer. So then I'll go to top layer, place polygon pour. Now it gives me some ability similar to the region that I just placed. I can now place the polygon pour. And let's just do this real quick. I'm being super careful about it, but you actually don't have to because it will respect the board edge, the board outline. Great, so now you can see there's a bunch of copper. Everywhere there's red, there's copper. So now we have a board filled with copper. Now I'm gonna wanna go to Design, Tools, Polygon Pour, Polygon Manager. And here all of our polygons show up. We just made this random one. We wanna make this the net ground. And let's give it some reasonable name like top layer ground. Apply that and it doesn't show up, but if we go here, it's giving you, what you need to do now is re-pour it. So you go to Polygon Pours, re-pour all. And now you can see it has poured itself. It's also connected itself to your ground pins. That's great. It's connected to ground. Great. So now say we want to do the same on the bottom layer. But what if you don't? What if you know that it's going to be the size of your board, but you don't want to draw it out like that? Because let's go to Tools, Polygon, Polygon Manager. You can create a new polygon from board outline. And it creates a new polygon here, so let's select it in the list. Oops, stop. And select the layer, make sure it's ground, and name it something. Great, and now we've got a polygon on the bottom layer without having to draw it out or anything. And now you see we have top layer, copper, bottom layer, copper. Now, when you're doing design, it's kind of annoying to have these copper layers in the way of your design. All you have to do is go to here and hit this shelve 2 polygons, or however many polygons you have. And it shelves them. It has not deleted them. They're still there. All you have to do is go back and restore them. And usually you also have to re-pour them. And there they are. they're back. So I think we've covered most of everything, all the basics. We've covered the basics, how to set up your board, how to, you know, all these things. This is, from here, it's sort of up to you to make good engineering decisions about how the components should be placed and what should go here and there and everywhere. So that will be a lecture or a workshop for another day. I think that's everything I wanted to cover. So I thank you for coming, and I'll wrap this up.